Welcome back, everyone. The search for helium-3 and rare earth elements on the Moon is one of the most ambitious undertakings in modern science and engineering. Many space agencies and private companies are beginning to outline practical steps for how these materials could be identified, extracted, and transported back to Earth, or used directly on the lunar surface. In this video, we will examine the methods that are being developed, the companies leading the way, and the technical challenges that must be overcome. Please subscribe now. The first focus is helium-3, a light isotope of helium that is rare on Earth but present in lunar soil at measurable levels. On Earth, the atmosphere blocks most solar wind implantation, so helium-3 does not accumulate. The Moon lacks this protection, which allows solar particles to embed helium-3 into regolith grains. Apollo samples indicated levels around 20 parts per billion. That seems small, but across large regolith volumes it becomes a significant resource candidate that merits careful prospecting for future energy research. Extraction of helium-3 starts with heating regolith to release volatiles. Researchers at the University of Wisconsin-Madison tested heating of simulants near 600 degrees Celsius and measured gas release. The European Space Agency ran similar experiments using concentrated sunlight to drive furnaces that achieve the required temperature. Gases released from hot regolith are routed through cold traps and compressors. They are then processed by cryogenic separation, since helium-3 and helium-4 have slightly different vapor pressures at very low temperature. This difference allows the lighter isotope to be enriched for storage. The lunar environment does provide advantages for cryogenic storage compared with Earth. Permanently shadowed craters near the poles remain below -150 to -200 degrees Celsius. These areas are colder than terrestrial freezers and can stabilize volatile materials with minimal boil-off. Tanks in such regions could retain helium or hydrogen with lower power input. By contrast, equatorial and mid-latitude sites swing from extreme cold to high heat, so insulated tanks and active cooling are required. This means site selection directly influences the design and reliability of storage facilities. Fusion designs help us understand why helium-3 is so important. Tokamaks and stellarators usually rely on deuterium and tritium, and these produce high-energy neutrons that damage the reactor walls over time. But a deuterium and helium-3 reaction mostly gives you charged particles and far fewer neutrons. This means you need less shielding, and it could make the materials challenges quite a bit easier. Companies like General Fusion and Commonwealth Fusion Systems are focusing on deuterium and tritium cycles for now, but they do see helium-3 as a longer-term option if we can sort out the supply. Understanding how to extract and store helium-3 today sets us up for the future, when fusion reactor concepts mature. Rare earth elements are also important. Neodymium, praseodymium, europium, and dysprosium are essential for permanent magnets, motors, turbines, and advanced electronics. Apollo samples, along with orbital surveys published by NASA, show there are trace amounts of rare earth oxides in both the mare regions and the highlands of the Moon. The concentrations aren't as high as the richest deposits on Earth, but the Moon's stable geology, without any vegetation or weathering, makes mapping a lot simpler. There's a lot of strategic interest here because rare earths support critical energy and computing hardware, and sourcing them from the Moon could help supplement or even protect supply chains for industries that depend on these elements. Processing rare earths from lunar regolith starts off with excavation and crushing. Robotic diggers, based on NASA concepts, would deliver the soil to processing hoppers. Then crushers work to create a uniform particle size. After that, magnetic separation is used to concentrate ilmenite-rich fractions where rare earths might be present. Chemical leaching comes next, using acids or ionic liquids. Early operations might need to bring reagents from Earth, but future plants could end up making simple chemicals right there on the Moon. Each step is set up to provide a steady feed for the next, so you get continuous operation and hopefully minimal downtime once everything's integrated into automated processing lines on the lunar surface. Private companies are gearing up to test these crucial steps. Over in Japan, iSpace is hard at work developing excavators and conveyance systems for those early missions. Meanwhile, in the United States, Astrobotic is busy with NASA contracts, focusing on payload lines for spectrometers, drills, and sample handlers. These instruments can map elemental signatures and return ground truth to validate orbital data. The mission schedules announced by these firms include flights all the way through 2026, aimed at studying ice-bearing soils and mineral-rich basalts. Data from such missions also informs rare earth targeting, since the same instruments detect multiple useful chemical signatures. The European Space Agency is advancing in situ resource utilization through molten regolith electrolysis. Concentrated sunlight is used to melt soil in a vessel, and then an electrical current separates oxygen from metals. This process not only produces oxygen for life support or fuel, but also leaves behind a metallic slag. Analysis of this slag reveals iron, titanium, and aluminum with trace elements. These residues can be remelted or sent to chemical separation lines to concentrate rare earths. The beauty of this method is that it avoids large volumes of water-based chemistry and utilizes sunlight as the main heat source, reducing the mass of imported power equipment for those early operations. NASA's Artemis program employs the Commercial Lunar Payload Services framework to fund prospecting and technology demonstrations. Instruments, including neutron spectrometers, are used to sense hydrogen, while drills collect samples and mass spectrometers analyze volatiles. The Volatiles Investigating Polar Exploration Rover, or VIPER, is set to map the South Polar region. Its primary focus is water ice, but its drilling and sampling provide a template for future payloads that will examine mineral content. This integration of instruments demonstrates how exploration missions create direct pathways toward resource identification and eventual pilot plant placement. Industrial helium-3 requires isotope separation at cryogenic temperatures. Teams at Oak Ridge National Laboratory describe systems where helium mixtures are cooled below 3 Kelvin, so very small vapor pressure differences allow staged enrichment. A lunar plant would compress the gas stream, pass it through cryogenic exchangers and separators, and circulate it with low-loss pumps. Continuous power and thermal insulation are required. Solar arrays with storage or small nuclear reactors can provide a steady supply. These designs must operate for long lunar nights where temperatures and power demand are highly variable. Transporting materials is another challenge. SpaceX reduced launch cost by reusing Falcon 9 and is testing Starship for heavy payloads. A lunar supply chain could load refined gases into dewars and mineral concentrates into containers, lift them on cargo landers, and transfer to a depot in orbit. Tanker stages would deliver to Earth orbit for re-entry or capture. Blue Origin is developing the Blue Moon cargo lander for surface operations. These logistics systems form the backbone of any mining economy, linking extraction sites with destinations for research or industry. Local use of products can improve economics. Helium-3 can support neutron sources and small research devices. Rare earths can form permanent magnets for motors and actuators. Researchers at MIT Lincoln Laboratory showed that printed electronic substrates using lunar simulants are possible. If rare earths can be alloyed into magnetic or optoelectronic parts on site, fewer assemblies need to be shipped from Earth. This reduces mass and supports longer operations. Local manufacturing is therefore a central strategy for achieving sustainable lunar activity and supporting ongoing exploration infrastructure. Costs remain high. Machinery must survive vacuum, radiation, and dust, which is no small feat. Maintenance requires sealed joints and modular design, making things a bit more complicated. Analyses in Science Advances estimate wide ranges for break-even helium-3 prices and stress uncertainty in concentration and processing yield. Rare earth grades are also lower than earth ores, which adds another layer of challenge. But counterweights include strategic value and the ability to use byproducts like oxygen and metals locally. These side outputs help balance economics by supplying propellant and construction material, reducing dependence on costly supply chains from Earth. Japan's space agency JAXA is advancing precision access. The smart lander for investigating Moon demonstrated pinpoint landing to reduce traverse distance. JAXA also supports compact drills and mass spectrometers for volatile detection. These systems integrate with Artemis and SA campaigns. Precision matters because it reduces equipment wear and energy demand, allowing smaller power systems to achieve results. Efficient access means prospecting can be completed with fewer resources, which shortens timelines and lowers cost for the first plants that attempt integrated extraction of helium-3 or rare earths. Heating regolith for helium-3 release requires careful energy planning. The German Aerospace Center examined solar concentrators that track the sun and focus light into reactor chambers. Ceramic-lined receivers absorb light and transfer heat to moving regolith. Trials with simulants confirm that the target temperature can be reached with practical mirror sizes. Designs must tolerate dust and thermal cycling, which is quite a challenge. Mechanical features include gimbals, shields, and radiators. Concentrator furnaces may reduce mass compared with electrical heaters, making them attractive options for early pilot plants seeking energy-efficient performance. Rare earth chemistry has unique challenges. These elements are dispersed at low concentrations, so systems must process large volumes. The Colorado School of Mines explored ionic liquids as extractants that work with less water and can be tuned to select ions. Experiments with simulants show promise, though scaling up needs corrosion-resistant vessels and closed-loop recovery to minimize resupply. Automation is essential since crew time is limited. Robust sensors and fault-tolerant controls will be required. These systems represent the next stage of laboratory work before deployment in space environments. Dust control is necessary for reliability. Lunar dust is sharp, charged, and abrasive. NASA tested electrostatic screens that clear dust from surfaces. Honeybee Robotics designs sealed excavation tools and enclosed conveyors to limit dust intrusion. Vacuum locks at transfer points can help processing areas stay clean. Each measure adds mass but reduces maintenance costs and downtime. Effective dust mitigation is critical for safe, long-duration operation. Without it, equipment performance would degrade rapidly in the abrasive and adhesive conditions unique to the lunar surface environment. Timelines are divided into near, medium, and long-term. Work through 2026 will focus mainly on mapping, drills, and ovens that measure energy use and gas yields. The late 2020s may see pilot plants heating tons of regolith and running separation columns. The 2030s could bring industrial lines if economics prove favorable. For Helium-3, progress depends on fusion technology. For rare earths, demand already exists and the advantage is clear. Each phase builds capabilities step by step, leading from science experiments to resource extraction with industrial applications. Private investment is entering the scene. Lunar Resources Inc. in the United States is testing molten regolith electrolysis under NASA awards. European startups are working with ESA to demonstrate oxygen plants that also create metal and slag streams for rare earth separation. These ventures complement government programs by targeting specific technologies. Combining public and private projects lowers risk and accelerates development. This model allows companies to scale hardware production and service repeat missions. Such collaboration will likely define the pace of resource development in the coming decade. Remote sensing directs operations. The Lunar Reconnaissance Orbiter mapped titanium and iron distributions using spectral bands. Future missions with improved hyperspectral cameras are planned with international partners. JAXA instrument teams are building compact sensors for small landers and rovers. Better spatial resolution links orbital data to ground truth and reduces uncertainty. This improves the odds that pilot plants will be built on regolith with the right chemistry for extraction. Remote sensing therefore guides efficient site selection and reduces wasted effort on unsuitable or low-grade terrain. Universities add new ideas. Researchers at ETH Zurich are studying plasma separation that vaporizes regolith and uses electromagnetic fields to sort ions. Although it's quite energy-intensive, this method could bypass aqueous chemistry and produce clean elemental streams. Advances in superconductors and more efficient power electronics may lower the energy cost. Collaboration with ESA facilities and national labs is supporting progress in this area. Ground testbeds that simulate lunar vacuum and temperature can help evaluate reliability. University partnerships also help expand the range of concepts under evaluation, so agencies and companies can select the most promising ones for scaling up. Helium-3 must be considered with realistic expectations. ITER and other major fusion projects still focus on deuterium and tritium, which have a much stronger experimental basis. Even so, developing extraction and storage methods now does build technical experience that could perhaps apply later. Rare earth efforts, on the other hand, have more immediate uses since existing markets need magnets and catalysts. A balanced program that produces oxygen, metals, and small quantities of rare earths for components can demonstrate sustainable operations. Such an approach shows value even before Helium-3 fusion becomes feasible. Storage of Helium-3 requires specialized tanks. Oak Ridge National Laboratory designed cryogenic vessels with multi-layer insulation and low-leakage valves for long-duration containment. On the Moon, such tanks would sit in shielded berms near processing plants and connect to transfer lines that load dewars on landers. Instrumentation would track pressure, flow, and inventory. Any loss is costly given the effort of extraction. Operating procedures really stress controlled fill, careful cool-down, and periodic inventory checks to ensure safe containment and efficient use of helium-3 resources. Strategic considerations motivate many programs. The European Commission has emphasized the importance of securing rare earth supplies for energy and computing. NASA and partner agencies have structured the Artemis Accords to set norms for responsible resource activity. Standards for data sharing and traffic management reduce risk. Industry groups can set common interfaces for cargo transfer. These frameworks help ensure safety while enabling competition and innovation. Strategic planning at national and international levels therefore plays a critical role in shaping how resource extraction develops. Integrated plants can raise returns by using every output. Heating regolith for helium-3 also releases volatiles, produces oxygen from minerals, and leaves slag that contains metals. Water can be split into hydrogen and oxygen for propellant. Metals can be cast into beams and plates. Rare earths can be separated for magnets and sensors. Researchers at the Max Planck Institute for Extraterrestrial Physics describe layouts where hot solids, gases, and slag move between units so that waste from one process becomes feedstock for another. Integration raises efficiency and reduces cost. As new missions fly, more data will guide resource strategies. NASA, ESA, JAXA, and private suppliers will deploy instruments and robotic systems that link orbital surveys to samples and pilot plants. Capabilities will progress from laboratory benches to lunar testbeds and finally to production lines. The pursuit of helium-3 and rare earths is ultimately about building the skills and equipment needed to use extraterrestrial resources. This work supports human presence beyond Earth while improving access to critical materials for energy and electronics. Thank you very much for watching. Please like and subscribe.